everybody. My name is Mridul, and today we are going to discuss about a topic which is called Fleming's Right Hand Rule. Okay. Now this topic is about electrical machines, how we apply this rule in electrical machines. Okay. First of all, we will understand why we need this. Okay. And second thing is, why is it important for the exam gate. Okay. Now the application of this rule is very important for us to find out the direction of induced EMF. Okay. Now induced EMF, if you see, we know that this induced EMF can be explained by Faraday's law. Okay. Now we also know that from Faraday's law, EMF can be induced in two ways. One is flux linking and one is flux cutting action. So flux linking is, example of flux linking is a transformer where a conductor which is cutting the flux will not move, but the flux or the flux that is linking the conductors will change with respect to time. When the flux changes with respect to time, then we have induced EMF in that conductor. Okay. So on that principle we have transformers. But here we are talking about the flux cutting action. That means if I have a flux, now that flux may be not changing with respect to time. But if there is a conductor which is moving in this flux or cutting this flux, then EMF will be induced in that particular conductor. Now our aim here is to learn how to find out the direction of induced EMF and in which direction the current will flow and why is that. Okay. Now on this principle you will have questions in gate. For example, there was a question in 2005 which we will show later. There was a question of in 2005 which was asked on this particular concept. Apart from this, it is very important, to understand this concept so as to understand various electromechanical energy conversion device, for example DC motors or DC generators, or specifically we are talking about generators where we will have induced EMF. It can be AC generators or DC generators. Okay. So now let's see how to apply this and how to find out the direction of induced EMF in the conductors. Let us take an example. Okay. So for example, I have North Pole and South Pole in this way, and I have a rotor here, and there are, say, conductors. There are 4 slots in the rotor and conductors will be placed in these slots. Now let us say these poles are fixed. Say these are fixed. And the rotor is rotating clockwise. Rotating clockwise. So there was a question, this was a question which was asked in 2005 in gate, and they asked that what is the direction of the induced EMF in the conductors C1, C2, C3, C4. Okay. So now let us learn how to analyze this particular problem, these types of problem. So for that we need to, one technique to solve this or to find the induced EMF is by applying Fleming's Right Hand Rule. Definitely there are other techniques also, but this is the best technique by which we can find out. So what is this Fleming's Right Hand Rule? So Fleming's Right Hand Rule means there will be 3 fingers of the right hand. One is the first finger, and then the second finger, and then the thumb. Okay, and what does this represent? So that is what we have to learn. Okay, so for example, the first finger. Now this first finger, which is this, now this represents direction of the field. So I will write it here. Direction of field. Now we need to know which will be the direction of the field. That means from North Pole to South Pole, and again whether it is outside the bar or inside the bar, how to take this direction. Okay, so not knowing this thing is not enough. So for example, I have North Pole and South Pole here. Now whether my field will be this side or this side, this is the thing that we have to learn. So eventually we will learn, but let us now figure it out. What are the different fingers means? Okay, for example, now comes the second one is thumb. The thumb in Fleming's right hand rule gives the direction of motion of the conductors with respect to the field. I'll write it again. Direction of motion, or sometimes we call it direction of force also. So we can call it in this way also, direction of motion of conductors with respect to field. Now this is very important for us to understand. Okay, now once we have these two directions, okay, so the third finger or the finger which is left, that is second finger actually. So the second finger will give us the direction of, it will give the direction of induced EMF. Direction of induced. Now we have to understand how to apply this. Okay, so let us learn. So what I will do is, first of all I will solve this particular example. Okay, so please note it down if you want to. So now what I am trying to tell is, first thing is the direction of the field. So you see here in this particular case, I have a North Pole and South Pole. So in which direction will I take the field? From south to north or north to south? So always we have to remember that direction of field will be from north towards south, but outside the iron bar. Okay, outside the bar. Okay, now here you see, now you may ask or you may think, where is the bar and what is bar here? You see, always we have to understand that this thing, that if there is a North Pole and South Pole, suppose there is a North Pole and South Pole, this is a magnetic bar. So what will happen is the fields will be something in this way. Fields are always in closed loop. So what will happen is, field will come out from this place. Okay, field will come out from here and it will come inside the bar in this direction. Okay, so in this case my finger or first finger will be in this direction. Okay, because it is coming out from the bar here. Yes, so this is the case. In this particular case what we will do now, you see, now in this particular case, north is this side, south is this side. So you may think that north is here, south is here in this particular case. So you may think that it will be in this direction because north is here, the north was here, so it is coming out this side. And you may think it should be in this side, but it will not be in this side. Why? Because this is a part of the stator or the core which is shown. Actually the core will be something like this. Now what happens is, the flux will flow in this direction now, along the core. Why? Because they will flow through the minimum reluctance path. Now we always know that, now this is my core, okay. Now we always know that my flux will come out from the bar, from north. So you see, it has to come out from here, from the north. So now you see, yes, placing my direction of the field will be this. So in both these cases, see, both are different cases. Okay, but in both these cases we have to see from where, from which point is my field coming out from the bar. So here this is my bar. You see here in this case this is my bar, and here the field is coming out. So I am taking the field direction as this. Here this is my bar. So this is my bar. In this case, it is coming out from this side. That's why my field is along this direction. I hope I am clear. Okay, so now let us proceed with this understanding. So what we understood is that my field will be along this direction. So this is my field. Okay, so this is my field. Now next thing is, so this is the first thing. The next thing will be direction of motion of the conductor. So if you see now with respect to field, now if you see, if a person sits here, what he will see is that this conductor is rotating clockwise. So we will take the instantaneous direction. Okay, instantaneous direction means at this particular situation, this conductor is moving this side, this is moving this side, this conductor is moving this side, and this conductor is moving this side. This case is simple. So that means now the C is the conductor or the direction of the motion, or you may say force, is along upwards for C1. So upwards means now we have two directions. The first how to take that is, now we'll apply the Fleming's right hand rule. So we know that field is in this direction. So first of all we'll take one finger in this way. Okay. I have seen sometimes students taking three fingers in this way and they try to align it along. Now it is very difficult to align yourself along all the three directions. It's very difficult. So the easy way is, one by one we have to open the finger. First one is we'll open this finger, and this finger will show the direction of the north pole to south pole. Okay, outside. So this is my field. Now I will see, I need to find out induced EMF for this coil. For this coil, the motion is upward. So I'll pick up my thumb in the up direction. Okay. Now I will open my second finger. You see in this side. Once I will do this and then this. Now ultimately I will open this third one. So once I open this third, I can see that it is going inside. Okay, it is going inside. Now how do we represent inside? Inside means cross. That means induced EMF here, it will be cross. Cross means it is going inside. Okay. What will happen to C3? This particular case. Now in C3 you see the field direction is this, and the force direction is also this. Now in this case what you will do. So now we have always understand that this Fleming's right hand rule, whatever field, this is always a cross product. Cross product. Now you see, if both the directions of field and the motion of the conductor is in the same direction, so the angle between these two vectors is 0. Now sine product, okay, or cross product is nothing but sine of 0. Now sine of 0 is nothing but 0. So what will happen is, we will have no induced EMF in this position. Similarly, now we will try to find out for C2. Now for C2, see the direction of force is down, field is this. So what we will do, field is this. Now force is not up, it's down. So we will change the direction. Now we will open the second finger. Now it is showing that it is coming out of the board. So if it is coming out, what we will do is, we represent it by dot. Okay, so it is coming out. Now for the fourth one, similarly, for the fourth one, field direction is this, and the motion is this, in this direction. So field is in this direction, and force is in this direction. So the angle between them is 180 degrees now. And again, sine of 180 is 0. Okay, so the induced EMF in C4 will be 0. So the answer will be C1, it will be cross, C2, it will be dot, C3 and C4, no EMF. So this is the answer. Okay. So this was a question in 2005 of GATE, okay, in electrical machines, and this will be the answer for this. Now this was a little bit simple. They might, increase the complexity. Now if you see, what is this? This is nothing but a DC generator. Okay, this is nothing but a DC generator. Okay. Now let us take some more examples and understand what if the situation changes. Can we apply this learning? Okay. For example, now this is one more problem. Now this is not a GATE question now. Now what we will do is, but questions like this may come. Now I will do an opposite thing here. That means, what I am saying is, my fields are rotating now. Okay, my field is rotating clockwise, let us say. And my conductors are static. Okay, again C1, C2, C3, C4. So now this is fixed. Rotor is fixed, or whatever this rotor is fixed now, let us say. And this North pole and South pole, okay, is rotating clockwise. Now what will be the induced EMF here? Now see, if you remember, this is an example of induction motor. Now induction motor, what happens is, we have a rotor at the starting, and these rotors are short circuited. So what happens is, we have stator. In stator we have rotating magnetic field, and the rotating magnetic field rotates either clockwise or anti-clockwise depending on what is the connection. Okay, so let us say that the rotating magnetic field is in the direction of clockwise. So what will happen is, first of all, there will be induced EMF. First of all, in the conductors of the induction motor, there will be induced EMF. Now when EMF will be induced, and then what will happen? Then current will be flowing in that conductors. Now once current flows in the conductors in presence of an electric field, then force will be applied in the induction, in the rotors of the induction motor, and induction motor starts rotating along the direction of the rotating magnetic field. So if the rotational magnetic field is clockwise, my rotor will experience a force clockwise. Okay, so this is the operation of a or the principle of working of an induction motor, three-phase induction motor. Okay. Now here my question is simple, that if let us say that this is fixed, and I have a rotor, I have a north pole and south pole which is rotating clockwise. So what will be the direction of induced EMF in these conductors? Okay. So now let us apply. So we know the first thing is, my field will be from north pole to south pole at a particular instant. Now let us say at this instant my north pole and south pole is in this direction. After some time it will go somewhere else. That is, let us not worry about that. But let us say at this point north pole and south pole is here. So at this point my field is in this direction. After sometimes it will change. Okay, after sometimes it will rotate in this way. But for this instant, that's why I am using the word instantaneous. So instantaneously, let us say my field is in this direction. Okay, so I got this first finger. Now I need to find out direction of the conduction or the motion of the conductor. Now here is the problem. Now you see my conductor is not rotating itself. It's fixed. It's not moving. So what will be the direction of the thumb? So that is the reason I have said that the direction of the thumb or direction of the motion of conductors is something which is relative. That means with respect to the field. Now that means if I am standing here and what I am seeing is I am moving in this side, but with respect to me, okay, with respect to me, what I will see that this conductor is going in the opposite direction. Now this might be somewhat difficult to analyze in this way, so it is simply in this way. Suppose there is a person who is sitting outside, okay, and there is a bus, okay, and you are sitting in a bus, and a person is sitting in a bus in this way, and the bus is moving in this direction, and there is a person who is outside the bus who is just sitting on a shop nearby the road. Okay, so now if the bus is going in this direction, with respect to this person who is sitting in the bus, he will feel that the person who is sitting outside in the shop, he is going in this direction. Okay, now this is called relative motion. So if we apply the relative motion here, that means my north pole is going clockwise. So my north pole will see that my conductor is going anti-clockwise. That means at this position, my thumb will be downward. So this is my field and my thumb is downwards. So the induced EMF at that position C1 will be outwards. Okay, outward means dot in C. Okay. Similarly for C2, what will happen? C2, it will be anti-clockwise. So this means this will see that he is going this direction. So upwards, so it is going inside. Okay, so motion will be inside. So induced EMF, direction of this. Similarly, this C3 and C4 explanation will be same as the earlier case. Here it will be 0, here also it will be 0, because sine of 0 and sine of 180 is 0. Okay. So these are the two cases, which is very, basic, and which we should understand how to find the induced EMF in a particular electromechanical and energy conversion devices. Right? Okay, it may be any. It may be DC motor, it may be AC motor, it may be anything. Okay, doesn't matter. We can take a third case also. For example, suppose now I have conductors in the stator, let us say. Suppose I have a conductor here and I have a conductor here. Let us say this is A and this is B. And I have a rotor inside. Now this is the example of synchronous machine. Now what happens in synchronous machine is, my rotor, let us say it is rotating along this direction. Okay. So what is the induced EMF at A and B? Okay. Let us take the North Pole and South Pole in this direction so that it's easier for me. So now you see the direction of field will come out from the north. So we know that this will be, the field is in this direction. So field direction is this. Okay. Now the rotor is rotating clockwise, but the stator conductors A and B is fixed. So with respect to this conductor is moving anti-clockwise. Okay. That means the induced EMF in B, this is the field, okay, and this is the motion of B upwards. So the field or the induced EMF in B will be inside. So here the induced EMF will be cross. Similarly here, this is my field and this is the direction of motion. So this will be dot here. Okay. So in this way we can find out the direction of the induced EMF in all the three cases. First one was a DC motor case. Second was a case of induction motor. This is the case of a synchronous. Okay. I hope this particular explanation will be helpful for you and for understanding the basics properly. With this, I conclude this lecture. Thank you.